I'd like to welcome everybody to today's webinar. My name is Frankie Rodolfi. I am the Vice President of Marketing for Climate Earth. And if you've joined us before, you know that our educational webinars cover a range of topics related to environmental business intelligence. If this is your first webcast with us, welcome. We're glad to have you. We're pleased you could join us and hope you'll enter the dialogue later on during the question and answer period. Our goal in these talks is to highlight practical information, usually scientific and technical in nature, on quantifying environmental impacts for business purposes. To do this, we invite thought leaders to share insights and their expertise that you can take back to your organizations. Today, we will examine solutions for total water management. We are privileged to have Dr. Inez Hua, a top expert on water and toxicity. She is a professor at Purdue University in both the School of Civil Engineering and the Division of Environmental and Ecological Engineering, and she's a scholar, a visiting scholar at Climate Earth. Dr. Hua will discuss methods for businesses to measure their total water use, both withdrawal and consumption, from both direct operational sources and indirect supply chain sources. She will also explore practical ways to interpret and mitigate the business risks associated with water use, such as incorporating water risk into the procurement process. A case study of Central Concrete's total water management will be highlighted, and we're all looking forward to that. So a bit of background on Inez. Dr. Hua's research and teaching includes the areas of aquatic chemistry, environmental sustainability, and environmental organic chemistry. Her scholarly publications have been cited over 750 times and have been highlighted in publications such as Business Week. She holds PhD and MS degrees from Caltech and a BA from University of California, Berkeley. Inez's presentation will take about 35 minutes, and then we're going to take your questions. At that time, Climate Earth CEO Chris Erickson will join us to help moderate. So now I'm very pleased to introduce my colleague, Dr. Inez Hua.
Thank you, Frankie. And I'd like to just say a few words about my visiting scholar experience here at Climate Earth. I am a professor at Purdue. I've been there for 15 years. And I started off in the research area of water treatment and water pollution. And I had a sabbatical this academic year. And one of my interests during my sabbatical was to stretch the research that I do into a different arena, supply chain environmental impacts, and to really see organizations on the ground and what they need. So I also wanted to talk a little bit about what we mean by total water management before I jump into the slides. So total means three things. There's the water that is consumed at facilities, there's the water associated with electricity production, and there's the water associated with supply chain, all the goods and services that an organization needs. So that's what we mean by total water management, and we'll talk about why those three pieces are important. So if you've signed up for the webinar, you're probably all very familiar with why water is a high-profile issue currently. So I'm not going to spend a whole lot of time talking about the why. We're going to focus on the solutions aspect to water management. But I do want to provide a fairly high-level picture for some of the stresses related to water and drivers for water management. So here's a map, and this is by the United States Geological Survey, USGS. And what it shows is that in different regions of the United States, we are consuming variable fractions of the renewable water supply. So the different shading in the legend, as you can see, represents different fractions of consuming renewable supply. So in certain regions, like the lower Colorado, we're consuming very close to all of the renewable supply of water, which obviously is a stress on the natural environment. As for businesses, there are pressures related to water availability, and it means that industries become vulnerable in their operations and in their supply chain. And a few examples to drivers include mandatory disclosure requirements, So for public companies, there are disclosure requirements for physical risks related to climate change, and water availability and quality are in that category. There is voluntary reporting. So there are organizations like CDP, GRI, WRI that allow companies to voluntarily report things like water consumption and water use. There's NGO assessment. Organizations like Ceres put out very interesting reports on corporations and their environmental impacts, including water consumption. There are supply chain stakeholders and internal operations that have an interest in water management. And there's also the area of business development. There are examples, at least half a dozen examples, where constraints on water limit the development of energy, and both are needed. And there are process needs that many businesses have that are related to availability of water as well as availability of high-quality water. So that's a little bit about the why we want to talk about water. And let me move on to terminology. So a little bit of terminology. This is quoted directly from the glossary of terms that the United States Geological Survey puts out. And it's important to think about consumptive use specifically for this presentation. So consumptive use refers to water that is removed from the immediate water environment. All right? So it's different, a little bit different than water that is used and then put back into a river, for example. Consumptive use is removed from the immediate water environment, sometimes referred to as water consumed. And total water use, as I alluded to earlier in the presentation, is Scope 1, Scope 2, and Scope 3. And these are parallel to the scopes that we talk about when we discuss greenhouse gases, for example. So Scope 1 water is water consumed at facilities owned or controlled by an organization or an institution. Scope 2 is water consumed to produce electricity owned or controlled by an organization. And Scope 3 is all the water consumed to produce goods and services to support the functions of an organization. And Scope 1 is sometimes referred to as direct or operational water use. Scope 2 and 3 collectively are referred to as indirect. So these terms are used a little bit interchangeably, but I think it's important to have some clear definitions, particularly as related to consumptive use versus withdrawal, for example. So let me quote and talk about some numbers that give you an idea of the magnitudes of the different scopes and why it's important to measure all of the scopes to accurately determine an organization's total water use. So this data is excerpted by a recent paper on direct and indirect water withdrawals. And these are for various U.S. industrial sectors. All right, so I've selected a few sectors just to illustrate how the ratios of direct and indirect water for a particular sector might vary and how it might be germane to your organization. So let's start with total water, and this is in billions of gallons. So we can go down and look at farming, for the farming and the fruit farming and the ranching sectors. You can see there are some fairly large numbers in terms of billions of gallons for that sector. Food services and drinking places obviously are a little bit further down. They would buy from some of the farming sectors. And I want to note that cotton farming is in units of gallons per dollar output. In the interest of condensing the table, all of these numbers are together, but the last row is in a different unit. Just keep that in mind as you look at the numbers and as we look at the columns. So that's total water. And then the next two columns allow us to compare direct versus indirect. And at the end, we'll look at the ratio. So the direct water consumption for grain farming, fruit farming, ranching, food services, and cotton farming. The indirect, in many cases, is a much more substantial number. Sometimes it's a bit larger. And then the column to really focus on is the ratio of the direct to the indirect. So for grain farming and fruit farming, the direct water is a much larger portion, right? It's a much larger ratio, On the other hand, for sectors like ranching or farming and food services and drinking places, the direct to indirect ratio is quite small. In other words, scope 3, in this case, is a very large contributor to the total water use in that sector.
We just got a question about whether the presentation will be available after the webinar, and the answer is yes.
So this is where we switch gears a little bit and talk about approaches and methodologies. And I want to emphasize that despite the importance of indirect water use, few companies currently measure or manage it. And we were able to conclude this from various reports, including one very interesting one that was released by Ceres in 2010, and it was a benchmarking study of 100 companies. And what they report is that none of the companies provided comprehensive data on their suppliers' water performance, and only 6 companies included any water accounting data with financial filings. What's also interesting in this benchmarking study of 100 companies is that they had a variety of industry sectors. So beverages, chemicals, electric power, food, home building, mining, oil, gas, and semiconductors were all included in this benchmarking study. So I think it is representative of a broad cross-section of different economic sectors nationally and globally. So why is it that gathering scope 3 and indirect water consumption is such a challenge? Well, one reason is that in order to make good decisions, an organization needs to have comprehensive data. And the next couple of charts are going to provide insight into why comprehensive data is difficult to gather in some instances, and a couple of methodologies to getting that data. This is a supply chain water consumption map for a hospital. And if you look at the map, the gray bubble represents the total freshwater consumption across the entire supply chain. And this is about 8 kilograms of water per US dollar. These are real numbers based on data from the US Bureau of Economic Analysis and the USGS. And I will explain in a few slides how we get these different factors. But just so you know, when you look at the chart, it's very nice and symmetrical looking, but it is based on real data. The sizes of the circles represent, or they are proportional to the water that each circle contributes to the total. So for the Tier 1 suppliers, shown in blue, if you add up all of the blue circles, you get the gray bubble. And as you're looking at the chart, you might notice in some of the bubbles there's a small dot. For example, in raw meat, there's a small green dot in the center. And that actually represents the direct water. So this chart is showing direct water and then the indirect and the total by difference. And I also want to make the point that only a small portion of tiers 2 and 3 are shown. So for tier 1, you can see that a big part of the water consumption in a hospital is probably due to their cafeteria services, right? There's raw meat, packaged seafood, poultry, cheese, restaurants, coffee, tea, ice cream, and so on, which probably supports the cafeteria, the meals for their patients, and for their staff. And then further down on the chart, there are other products, diagnostic substances, plastic products, drugs, which serve the core function of the hospital. But what we tried to do was trace back water consumption through the different tiers of the supply chain. So the hospital buys meat, and then to produce that meat requires cattle, raw meat, fish, electricity, others, right? So that's tier 2. And then going further back to get the cattle in tier 3, we see there's grains and cattle also involved in making the cattle. So keep in mind that each of the bubbles in tier 1 could be expanded out to tier 2, and each of the bubbles in tier 2 could be expanded out to tier 3. So the entirety of the supply chain for this hospital is extremely complex, and the suppliers probably interact with each other. So there are multiple suppliers for many categories. These are economic categories shown in each bubble. So you can imagine, for example, drugs in Tier 1 actually would involve probably more than one supplier or one vendor that the hospital has to work with. And finally, what I find an interesting insight from looking at the chart is that core function purchases aren't major contributors to water consumption. So if a hospital decision maker were looking at this chart, they wanted to reduce water by a certain percentage based on procurement decisions. The good news is they could make those procurement decisions probably with purchases that are not core to healthcare, right? So healthcare probably involves diagnostic services, plastic products, and drugs, and not ice cream, right? We all like ice cream, but it's probably not core to the healthcare function of the hospital. And those three purchases are relatively small water contributors, at least for Tier 1. So that's a supply chain map for a hospital, which provides primarily services, right, to the consumer. Let's contrast this map with an organization that produces goods. So the next supply chain water map is for an automaker. And again, this is for an automaker in the US based on actual data. And note that the gray bubble is total water withdrawals across the supply chain. It's a little bit higher than for the hospital, 14 kilograms of fresh water per US dollar. Also notice that the direct water consumption for the automaker is a bigger part of the total, right? So that blue bubble in the middle is the direct, much larger than what we saw for the hospital, which primarily provides services. So there's Tier 1, and not surprisingly, auto parts are a big contributor to the total water consumption of an automaker. But there are some other interesting insights to be gained as well. After auto parts are leather and carpet, and then following that are a number of other parts that you could imagine would go into an automobile. Tires, glass, fluid meters, etc., paint. So if we go beyond auto parts and look at leather and carpet in terms of material selection, right, a decision maker might consider an alternative to leather seats, for example, in their auto if they wanted to try to reduce water consumption. This would make more sense than, say, carpet. It's harder to build a car without carpet than it is to swap out leather seats for a different type of seat covering, right? Some of the other components of the car would be harder to substitute, and so leather, with its relatively large water consumption and the fact that it might be substitutable, might be a candidate for an automaker. What's also interesting about this chart is we're going to trace back leather through 4 tiers of the supply chain to see how that water consumption is allocated through the different tiers. So let's take a look at Tier 2. Auto parts, as you can imagine, is fairly complicated. It includes auto parts, electricity, iron and steel is a big part of auto parts, and many other components like textiles, plastics, fabricated metal, etc. Leather can be primarily traced back to animal slaughter in terms of its large water consumption. Right? And if we in turn then take a look at Tier 3 and Tier 4, you can see that animal slaughter traces back to cattle as the largest water consumer in Tier 3. And then cattle can be traced back to crops to feed the cattle, grain, and other inputs from Tier 4. The iron and steel, in turn, in the Tier 2, which we're tracing back from auto parts, also traces back to a number of other different components. What's interesting is that electricity shows up in all of the tiers, and that would make sense. There are certain resources that are necessary for all of the tiers of the supply chain, and certainly energy is necessary to make just about everything. So electricity shows up a lot in the map, and this, again, emphasizes the complexity of the supply chain and the fact that if you want to engage suppliers directly, there are many different tiers, some of which an organization may not be able to engage directly, And even with Tier 1, there are probably many different vendors that this automaker would have to work with for supplier engagement. So with that in mind, with the complexities of the supply chain in mind, let me talk about some approaches to measuring Scope 3 water consumption, because measurement comes first and then the management approaches. So the three primary methods available are input-output or process-based life cycle assessment, or a hybrid of the two, and supplier surveys. And all of these methods are related, and they all have upsides and downsides in terms of gathering the data, the comprehensiveness of the data, and the time required by the organization, as well as the science behind each methodology. So input-output LCA, which I'm going to focus on for this presentation, explicitly links economic activity to environmental impacts. And it is a merging of the economic accounts for a country with the natural resource accounts. So the input-output databases for the United States include the Comprehensive Environmental Data Archive, EIO-LCA database, and OpenIO. All of these databases include data for over 400 commodities and services. And the data sources include the Bureau of Economic Analysis, for the environmental accounts, the US EPA, USGS, and many other federal agencies. So this is national data, national environmental data that's merged with national economic data. And the economic accounts capture transactions, between all of the different sectors. So they're a good picture of who's buying and selling to whom. And I also want to emphasize that what we're talking about are environmental impacts of materials extraction and manufacturing included. So it's a cradle-to-gate analysis. And let me give you a very simple example of how we would calculate for one purchase the environmental impact. So the methodology that I'm going to discuss is a combination of an organization's financial data, such as procurement, combined with the data in the IO database, which then provides Scope 3 water consumption. So if an organization purchased $1,456 worth of item X, and the factor was 1.2 kilograms of water per dollar, then the total Scope 3 water would be, as you can see, 1,742 kilograms. So I highlighted that factor in blue because it comes directly from merging economic activity with environmental impacts. That's the value of the IO databases, is that we get these factors, these environmental impacts per dollar of economic activity, which then allows us to merge this information with financial data. So let me talk a little bit more about total water use data collection. And this is an iterative process where we do some screening, and then based on the initial screening results, we refine and sometimes collect a second round of data. So to get direct water, we can base this on water purchases or production. Often organizations will have, they produce their own water to use on site, minus the discharge, right? So this is to get direct consumption, water purchases and or production minus the discharge, which then allows us to calculate Scope 1. So all of these are hypothetical example numbers, right? So there's some substitution, for example, based on the dollars per gallon that someone pays, or based on meter readings. Those would be data sources for direct water. And as you know, it takes water to make water, so we can also calculate the Scope 3 water of water purchases. For electricity purchases in the United States, there are water factors that have been published by NREL, the National Renewable Energy Lab, that allow a conversion of kilowatt of power delivered to the customer to be converted to kilograms of water consumed. Right? So based on electricity purchases, we're able to calculate Scope 2 water. And then, of course, materials and services, which I highlighted in the previous slide. We have purchases of fabric or insurance or transit or any other type of purchase that you can imagine an institution would make. there are water factors that then allow us to convert dollars to water consumed. So that's the methodology for total water use, the 3 scopes. And let me now move to a case study with Central Concrete, where we apply the methodologies and the approaches that I've discussed for the first part of the presentation. Central Concrete Company is a major supplier of ready-mix concrete and building materials, and it's a division of U.S. Concrete. For this case study, the company provided financial data from 26 profit centers in the San Francisco Bay Area. That included 14 batch plants and 4 stores locations, and they also provided utility logs. What's interesting is that this is an extension of the GHG calculations that the company has completed over the past few years using the same methodology that I outlined, except for greenhouse gases rather than water. And as an extension of this study, they also calculated their scope 1, 2, and 3 water consumption. So now there's a systematic way of integrating more than one environmental impact, right? There's a way to look at GHG and water consumption as well, which we'll do a little bit with the case study. And in general, concrete is an important construction material, and any opportunity to reduce environmental impacts is desirable. So let's take a look at the numbers. For Central Concrete, the overall water consumption was 180 million gallons, and this is for the 2010 year. The Scope 3 water was the largest, 77%, followed by Scope 1, and then Scope 2 from electricity production. The water intensity per cubic yard of concrete ranged anywhere from about 140 to 185 gallons of water per cubic yard. So this is company-wide within Central. And it's an interesting and good verification of the table that I showed earlier in the presentation, where we compared direct and indirect water from many different sectors. And what this shows is that this company, with its various purchases from different sectors, right, still has a Scope 3 indirect water consumption. That is the majority of the total. 77% of their total water consumption is due to their purchases and supply chain water consumption. So it's a good verification of some of the national average data for sectors that was shown earlier in the presentation. What's also interesting is that this company can now compare the different scopes and the total water consumption at the various plants that they maintain. So even though company-wide, Scope 3 water is the majority of the total water, it does vary a bit depending on the plant, depending on the operations. And this variation means that the plants might choose different strategies for reducing total water at their specific site. So if you compare the Stockton plant, where 79% of water is Scope 3, compared to Oakland 5th Avenue, which is 69%, if there were, say, a 10% reduction goal, the different plants might approach this differently. So they could take process or other operational changes, right, which would affect Scope 1 water, energy conservation, which would be Scope 2 reduction, which would involve the electricity consumption at the plant, or they could make procurement decisions that would reduce Scope 3. Or they could choose a combination of all three, right, to meet some sort of reduction target. So let's take a closer look at the Scope 3 water in the Stockton plant consumption. So this is water consumption by plant and also material detail. So the slightly bigger pie chart is what you saw on the previous slide. It's just the total water consumed at the plant, Scope 1, 2, and 3. And then the big 79.1% wedge has been broken down by materials. So this is Scope 3 water by materials. And the percentages that you see are actually a percent of the total. They're not a percent of the 79.1. That's how the numbers work out. So you can see that the top contributors actually fall into maybe 8 categories, right? So a large contributor here, about 21%, is fine aggregate, purchases of fine aggregate made by Central. Cement, the second largest. At 15.5%, the third largest is coarse aggregate. And then as we get into some of the smaller categories, this is slag cement at 3.9%, and so on. So you get a sense of the different purchases that are contributing in a large way to water consumption. These are not terribly surprising for a company that makes ready-mix concrete. But I want to emphasize that this type of analysis could be applied to just about any organization, whether you manufacture or not, right? There would be different sites for which you could calculate the different scopes of water. You can drill down into Scope 3 and then look at what material purchases are contributing to most. So you can imagine this pie chart really with pretty much anything, any type of material analyzed for water consumption. So I mentioned GHG and water, and of course climate change and energy and water are often discussed in parallel. And I think organizations are just now thinking about integrating different metrics and balancing metrics to make decisions. So what I have on the right-hand side of the screen is the GHG impact for the Oakland 5th Avenue plant. All right? And then for the same plant, on the right-hand side, is the water. This is total water compared to total GHG. You can see all scopes. And the GHG impact is very much dominated by Scope 3, 95%. So it's even more dominant than the Scope 3 water. And I would say that in thinking about water reduction strategies at this plant, there are probably more choices that the company could choose from, right? So say for a 10% water reduction or a 10% GHG reduction at the Oakland 5th Avenue, there are more choices to be made with the different scopes, right? That 10% could come out of a couple of different scopes in terms of water, whereas with GHG to reduce by 10%, probably the best strategy is some kind of procurement change. So that's one comparison and one way to think about GHG and water in tandem when making reduction decisions. Another interesting insight that Central can now make after it's done its own study, right, looked inward at its own operations, is to benchmark versus an industry average. And this can be valuable for a lot of reasons, strategic as well as operational. And this first chart is an industry average of water and GHG for ready-mix concrete. This chart was generated with input-output data, so it represents U.S. national averages. And you can see that for GHG, the dominant contributor is cement. That's the light blue, right? GHG, cement, 70% of the total GHG for ready-mix concrete comes from the cement. A smaller portion comes from the water consumption. And there are different commodities that contribute to making the ready mix. So it's not surprising that they would be different for GHG and water. But the take-home actually is in terms of the Scope 1 and 2 benchmarking. As a percentage of the total water consumed, Central's Scope 1 is actually less than the industry average. The industry average looks like about 30% Scope 1 for total water consumption to make ready-mix concrete, and Central's is about half of that. And it's slightly higher than the Scope 2 average. I would say it's comparable. So that's very valuable, and we could do the same thing with all of the different categories, right? We could drill down into total water consumption for the company and compare it, for example, for truck transportation national average. And this gives insight into different categories and different areas of the operation that could be targeted. And now that we've talked about quantifying the magnitude of consumption, I also want to talk a little bit about what it all means in terms of environmental impact. So quantifying the volume of water consumption is only the first step in thinking about how to manage it and what it means. And in LCA methodology, characterization is a key step towards analyzing environmental impacts of resource use. So we're going to talk about characterization and a little bit about damage further along. What's interesting about water compared to GHG, for example, is that characterizing consumption quantifies the location-specific nature of the impacts of water use. And I'm going to show you some maps that will illustrate this and really bring the point home. One approach to characterization is to apply the water stress index, or the WSI. And this was developed by some researchers in Europe, which I will reference in the next couple of slides. And conceptually, water stress is calculated from withdrawals to hydrologic availability, WTA. WTA is a ratio of the total annual freshwater withdrawals to hydrologic availability, WTA. You calculate WSI from WTA. And then you do a simple multiplicative transformation. So the WSI number, which ranges anywhere from about 0.01 to 1, is multiplied by the water consumption volume. So for Central's Scope 1 water, with the location numbers, we were able to characterize that based on a WSI for their locations in California. And this map is a plot. It's from a paper that was published in 2009 by Pfister, Kohler, and Hellweg of WSI values globally. And the point of this is that water consumption impacts are very location specific, depending on the availability and demand in a particular region. So as the colors become darker, the WSI becomes larger and larger. It ranges from less than 0.01 to up to about 0.9, the more water stressed a region is. All right, so there's the water stress index, and then there's the consumption, and those two together contribute to the magnitude of the impact and the potential damage. And I'm going to show you some more state level, more local level WSI data that's actually available as a Google map layer from these same researchers. It's based on the research that they've done, but it's a Google map layer. And so for the purposes of continuing the thread related to Central, let's think about the WSI in California versus Michigan. And this would affect any company with national or global operations. Right? So in California, you can see some of the numbers for WSI, 0.016, which is a fairly low water stress index area up in Northern California near the Oregon border. And most of the state actually is pretty water stressed, not surprisingly, right? So the WSI values are close to 1 or they're 1. That's probably a rounding that Google Maps does. So California, Nevada, the bordering states are fairly water stressed, although it does vary even within a state. You can see that the center of Nevada is less stressed than other areas in the state. So let's look at Michigan. Now, on this map, you don't see any numbers, but I can assure you that most of Michigan has a fairly consistent and a fairly low water stress index. So for the purposes of comparison, let's think about two facilities, one located in South San Francisco, another one located in Detroit, Michigan. So the WSI for South San Francisco is 1, approximately 1, and for Detroit, it's 0.0348. Or in terms of percentages, it's about 3.5% of the value in California, so much lower. So we can use those WSI values as a way of furthering the analysis of what water consumption actually means. So you can think about a cause and effect chain, right? Stressors and endpoints, and think about water as being a stressor to the natural environment. So what are some of the endpoints of that stress? So water consumption, we characterize it with the WSI values, which I showed you on the two maps. And then a couple of examples of endpoints based on the ECO Indicator 99 framework include damage to resources. So in terms of water specifically, one way to think about damage is the amount of energy required to make the depleted water available in a region, right? So this is the amount of energy required. Ecosystem quality, which is based on damage to vegetation. And there are implications for biodiversity as well when it comes to ecosystem quality. And that's because plants are a crucial base for ecosystems, right? So what damage does a particular volume of water consumed do to the ecosystem? You can quantify this with these methodologies. And then human health. And in the ECO Indicator 99 model or framework, human health refers specifically to malnutrition because it's based on the concept that agricultural irrigation is displaced when other users consume water in a particular region. So what damage is there to human health because of displaced irrigation, which then impacts food production? And you'll see that these damages are going to vary a lot globally. It's not just WSI. So there are factors for estimating the damage associated with water consumption, just like there are multiplier numbers corresponding to WSI. So let's work through a sample calculation. I'm a professor, so I have to do a sample calculation in a few slides. But first, let's look at the variation. So the first chart, this is again figure 2A, that you've seen before, is the WSI. Now compare that to the ecosystem quality map, which is figure C. And it's interesting if you look specifically at the United States. The WSI values, there's a lot of water stress in the western half, not so much the eastern half. But the ecosystem damage, even in an area of the United States that isn't necessarily water stressed, is actually fairly significant, right? If you look at the western and eastern halves, the ecosystem quality damage is spread out across the United States. And globally, there are differences in terms of ecosystem quality. So for central concrete, and there's scope 1 water consumption in California, the potential damage due to that consumption is primarily in ecosystem quality and resources, and very little damage to human health, right, which I'll show you in the next set of maps. So this is the map that shows resource damage as well as human health. And you can see that for most of the United States and Canada, the damage due to human health based on water consumption or water stress is actually fairly low, right, compared to other parts of the nation. There's little damage to human health. So if you look at figure 2D, right, human health, figure 2D is where you see that most of the United States and Canada will not impact its citizens due to water consumption and human health impacts. And then figure B above shows the resource damage in terms of the amount of energy it would take to replace the fresh water that was consumed, right? So the resource damage seems to be focused more regionally than human health or ecosystem quality. All right, so let's do a little example where we show how you can go from consumption to potential damage. And let's consider a facility that consumes 1,000 cubic meters of water in South San Francisco, California. So this is where Central Concrete has one of its facilities. So 1,000 cubic meters times the WSI value, which is 1 in South San Francisco, gives us a volume, a characterized volume of 1,000 cubic meters. We can then take that volume and multiply it by a factor that relates to ecosystem quality, and you get 243 square meters per year. Now, to keep this in mind, recall that ecosystem quality is related to damage to vegetation, right? So we're talking about a surface area of damage to vegetation that results from water consumption. The resource use would be 1,000 cubic meters of water consumed, right, multiplied by a certain unit energy per unit water consumed. So MJ stands for megajoules, all right? That's the resource damage. And this method is a nice way to compare endpoints across different areas of the world. All right? Now let's contrast that with a facility that consumes 1,000 cubic meters of water in Detroit, Michigan. So 1,000 cubic meters times the WSI value, which was 0.0348, much smaller volume, right? The ecosystem quality factor is actually 0 for Detroit, Michigan. And the resource damage factor is also much smaller, so about 108.1 megajoules. And by the way, these numbers for the ecosystem quality and the resources are also available on the Google Map Player, and they are published as well in the paper. So these are numbers that are available in the scientific literature, and they were based on extensive data collection and modeling in each region for which they've been calculated, all right, based on actual precipitation data, land cover data, and then modeling as well. So a company that has locations throughout the United States can quantify reduction in potential damage in each state resulting from the same reduction in water consumption, right? So if you're a company with national or global operations, the same volume of reduction in water consumption at one site could actually reduce damage more than the same reduction at another site. And if you're trying to reduce multiple environmental impacts at once, right, balancing GHG in water, for example, company-wide, you could take different strategies at different sites with each of those environmental impacts for a total reduction. So let me end with a couple of conclusions. First of all, understanding total water consumption requires quantifying scopes 1 through 3. And for central concrete, this calculation helps identify reduction strategies at specific facilities and for specific material groups. Water use is an environmental and a business risk, and any institution of significant size should begin to measure and understand both their direct and the supply chain use of water. Given the location-specific nature of water consumption, companies should identify points of water vulnerability, both in their own managed operations as well as in their extensive supply chain. And organizations should incorporate water risk into the procurement process. Strategies could include portfolio diversification or gaining commitments for reduction from key suppliers. And now I think we're ready to open it up to questions.
Thank you, Inez. We do have a few minutes left, and we're going to try to get, there are a bunch of questions already on our panel. We're going to get through as many of these as we can, and then any questions we don't get to right now, we will follow up directly and individually with everyone. So joining us now is Chris Erickson, the CEO of Climate Earth. Chris, did you pick one out that you want to start with?
Well, we have quite a few, as you said, so I'm going to start near the top and just take every other one and see how we do. Let me start with a basic one going back to the bubble charts, Inez.
Yeah.
That's how do you define tier 1, 2, 3, 4, et cetera? And that came from Mark Dillon. Talking about what are the tiers.
Okay. So tier 1 would be suppliers from which an organization buys directly. And then the tier 2 suppliers would be organizations that supply tier 1, and the tier 3 would supply tier 2, and so forth.
Got it. So this one has to do with the maps, I believe, that you were showing, the WSI stress index maps.
Yeah.
And the question is, do these survey data exist outside of the U.S.?
Yes, the WSI maps are available globally. In fact, I showed a map that showed WSI values for other countries besides the U.S.
That may have come in before you showed that.
Okay, yes, they are available. It's a Google layer. It's available widely in the scientific literature. So yes, that data is out there.
So this one's a little more detailed, and it has to do about hybridizing the input-output model. And the question is, how do you account for volume discounting, different pricing, when applying the water per dollar in quantifying the water footprint? That is, one company may pay 50% of the price than another, and which company would result in a 50% lower footprint. I think this has to do with sort of mapping and then looking at the key areas and drilling in.
That's a really good question. So let me take that from the first from the standpoint of direct water. When we worked with Central to calculate the direct water, we got the information, the volume information, directly from their meters. So we read off the meters, and then we were able to verify that based on purchases. And then there's a conversion where you have a metering rate and a total purchase, and you can figure out dollars per gallon. So that's how we did the the Scope 1 water. Scope 3 water is a little bit trickier because, of course, it is based on national averages that are supplied and put into the database.
Okay. Let's see. 31. This one is, it says, on the U.S. map, most of the industrialized states have better ratios than the agricultural ones. Is it due to greater availability of water or the better efficiency in industry as opposed to agriculture? In all your examples, Tier 2 and 3 were leading to agriculture also as main consumption use. Could we draw the conclusion that U.S. should increase its industry sector and reduce its agricultural sector? It's a lot of questions, actually, isn't it?
What map are we referring to?
I think we're talking about this stress map, and it says most of the industrialized states have better ratios than the agricultural ones. So is that a proper conclusion, and is it due to greater availability of water or the better efficiency in industry? Is there any trade-offs here?
Well, I think what we're talking about is the western half of the United States and the eastern half of the United States.
Yeah.
And what contributes to the water stress index is not just industrial use, but remember population. So the West, some of the western states are extremely densely populated, which also contributes to the water stress index. And there's simply less water. The precipitation in Arizona or Utah or Nevada or California is much less. And sometimes groundwater stores are much less. So it's not just the industries, right, that are contributing to the consumption, which contributes to WSI. A number of other factors also contribute.
So there's a number of questions here about the use phase. And most of them are related. So I'm going to try and sort of summarize them. But really, this one says still would like to know about product use impacts and how would you handle that, since it wasn't directly addressed in the presentation.
Absolutely, very important. So let's take apparel as an example. And we actually have some great bubble charts that we weren't able to show that trace apparel water use back to natural fibers such as cotton. But I can certainly understand that the use phase of apparel, where you wash, right, the consumer washes the apparel every time they wear it, that would contribute to impacts as well. And I think what we have to do to approach the use phase is work on different approaches to getting consumer data, consumer habit data that would then be added on to what we can calculate with our input-output methodologies. So the use phase is absolutely important, but I would say so are the upstream activities that lead to that product.
So really what it requires is market survey data or other types of data about customer usage, and then we can calculate, the impacts can be calculated from those numbers.
Yes.
Okay. How are we doing on time, Frankie?
Well, we got about two or three more minutes. Why don't we see if we can get a couple more in?
This is an interesting one. Is there any long-term link or connection from resource damage to human health damage? Or is this a graduate student program?
That's probably a dissertation. That is a great question because, of course, when we talk about, was it resource damage?
Yes.
And human health?
Resource damage, is there a long-term connection between resource damage to human health damage?
I would say not, because the human health primarily is focused on malnutrition, right? The consumption of water for other uses besides agriculture, whereas the resource damage is quantified by thinking about how much energy we would have to expend to replace the water that's consumed. So there is not a really direct long-term. There could be a connection between ecosystem damage and human health because, of course, ecosystems support almost everything on the planet, including food production. So there could be a connection there, but not so much between resources and human health.
So this last one is also, this is more detail about the water stress index. And the question starts by stating, those WSI numbers don't take into account plumbing, i.e. bringing water from elsewhere, right? That's a question. So for example, LA gets plenty of water from the Colorado River, but it's still characterized as water stressed. How do we account for that? Do we know how that plumbing sort of factors into the stress table? Do they count, or is it mostly weather-based? Or is there anything we can say about that?
That's a really good point. I will say, though, that there are a few states, I would say, let me turn it around. Most states are an exception to that. It's only in a few of the western states where we convey water over large distances. In most of the U.S., for example, the water is used directly. It's very close to the source. The user is very close to the source.
So we, sorry, Inez, did you want to?
No.
So we do have more questions that we're not going to get to right now, and Inez is going to, and I are going to help follow up with all of those. But before we wrap up, Inez, I just wanted to ask you where you see your research going, having focused on water and toxics and then spent this year with us here at Climate Earth.
I think the next step to this is actually to think about emissions to water. When we talk about water footprinting, for example, it's not just the amount of water that's consumed, it's also how that water quality changes once it's discharged back into the natural environment. So actually, Scope 3 water emissions is one thing I'm very interested in.
Great. We're looking forward to that, too. Well, that is going to have to conclude our webcast for today. Thank you, Inez. We really appreciate it. And
thank you.
Thanks to everybody in the audience for attending. There were questions about this. If you'd like to watch this webinar again or share it, yes, we will be making a recording available on our website in the near future. And also, if you want to learn about Climate Earth's environmental business intelligence systems or download a white paper about quantifying water, please do that from our website at climateearth.com. Thank you, everyone. See you next time.